So in this section, we're going to be studying these things called recurrence relations. And a recurrence relation is essentially any sort of sequence whose subsequent terms are going to be based on the previous terms. In computer programming, it's essentially the same thing as recursion. So basically what you do is you have iterations and you just go through, and each iteration is contingent upon the previous iteration. A lot of times we have to be given these initial conditions. In other words, what's the very first instance, just like in a computer program. So I wanted to show you a few examples of just how to work through a recurrence relation if I give you a recurrence relation and then also an initial condition. So for letter A, we have this sequence a sub n equals 3a sub n minus 1 minus 2. And the initial condition is that the first instance is going to be 0. So for letter A, we know that the first instance a sub 0 is going to be 2. Now, A1, which is the next item in the sequence, is going to be 3 times a sub 0, and that's the previous iteration. So all we're doing is we're just taking 3 times the previous iteration minus 2, which is 3 times 2. So all we're doing is we're just taking the previous instance, substituting it, minus 2, and that's going to be equal to 4. And then we're just going to continue in this fashion. So A2 is going to be 3 times the previous instance, which is 4 minus 2, and that's going to give us 10. The third, or a sub 3, which is actually the fourth term in the sequence, is going to be 3 times 10 minus 2, and that's going to be 28. And then we have a 4, which is 3 times 28 minus 2. 3 times 28 is going to be 84 minus 2. That should be 82. And then finally, a 5, which is actually the sixth term, because we would have 1, 2, 3, 4, 5, 6 terms. Notice that a sub naught is the first term in the sequence. So that's going to be 3 times 82 minus 2. 382s is going to be 246. 246 minus 2, 244. All right, so those are the first 6 iterations, or the first 6 terms of the recurrence relation. A second example where we have 2 terms within our recurrence relation. So in other words, we have to go through and be able to spit out a recurrence relation based on the 2 previous terms. All right, so the good news is that we already know B0, which is the first term, and B sub 0 is going to be equal to 2. And then B sub 1 is negative 2. So those are the first 2 terms in the sequence. Now to get B2, that's going to be equal to, I'll just write out the first one, 2 times 2 iterations ago, which is B0, plus 1 iteration ago, which is B1. So in other words, B2 is going to be equal to 2 times 2 plus negative 2. Right? And that should work out to just be 2. And then we can figure out the rest of them. All right, so let's go ahead and figure out B3. B3 is going to be equal to 2 times 2 iterations ago, which is B1. So 2 times negative 2 plus the previous iteration, which is 2. Okay, so notice what I did. I just took B1 and I substituted B1 directly into 2 iterations ago, and then I substituted 2, which is the previous iteration. Just because there's a lot of 2's, I want to make sure that I'm explicit with this, and this should work out to be negative 2. All right, so I'm going to circle these because these are the answers. B4, 2 times 2 iterations ago, which is 2, plus the previous iteration. So 2 times 2 is 4 minus 2 is 2. And then finally B5, which is the previous, the final iteration. That's going to be 2 times 2 iterations ago, which was negative 2, plus the previous iteration, which is 2. So B5 is negative 2. And what you'll notice is with this sequence, with this recurrence relation is that it just toggles back and forth. So notice that the first term is 2, the second term is -2, the third term is 2, the fourth term is -2, the fifth term is 2, the sixth term is -2. So in other words, what we have is we have an oscillating sequence. Okay, you may remember that if you in Calculus 2, you have that alternating sort of sequence. This is more of an oscillating sequence. It just oscillates between two values, meaning that the limit would never exist. So one of the things that we're going to be looking at specifically in this section is how can we take a recurrence relation and maybe turn it into a closed form or an explicit form of a sequence. So we don't like recursion. Recursion is extremely expensive when it comes to runtime in computers, and it also takes a lot of brain power. However, if we can get into an explicit form, that would be really nice. So one of the things that we're going to be doing is we're going to be working and we're going to be cycling between a sequence in closed form and a recurrence relation. So one of the things that we want to do is if I give you the solution, in other words the closed form, I want you to verify that it satisfies a recurrence relation. Now later what we're going to be doing is we're going to be taking a recurrence relation and we're going to be turning it into the closed form. Okay, that's a lot more difficult. So all we're going to do is we're just going to substitute k and k minus 1. So a sub k, if we substitute, right, so we're just plugging k in for 3n, that's going to be 3k plus 1. Right, so notice I'm just substituting the index k, and that's going to be equal to 3 times k minus 1, and then we have the plus 1. Okay, so all I did was I just substituted k minus 1 back in for n, and then I'm going to add 3 to that. Now clearly if we simplify this, 3k plus 1 is equal to 3k minus 3 plus 1 plus 3, and we get that 3k plus 1 is equal to 3k plus 1. So indeed it satisfies. So again, all we're doing to be able to verify this, let me erase all this stuff up here, right, is we're just substituting whatever the index is, or the subscript, so k, we're substituting it back in for n, right? And then we're substituting k minus 1 back in for n. So that's how these work. They're not meant to be too difficult, just substitution and a little bit of algebra. A second example. Here's our solution, our sequence, and what we're going to be doing is we're going to be substituting k and then k minus 1 and then taking the opposite of that. Okay, so b sub k, so this is going to be our right hand side. I'll just do this. So that's minus 1 to the k over k factorial. And then we have the opposite. We're going to substitute k minus 1 back in. So that's going to be minus 1 to the k minus 1 divided by, we're going to substitute k minus 1 back in for n. So that's k minus 1 factorial. But then we also have to divide by this k that was given to us. Now what we want to do is we want to simplify this expression. All right, so after a little bit of algebra, this negative, we can rewrite this negative out front as negative 1 times negative 1 to the k minus 1. And then notice that we have these two terms. We have k minus 1 divided by, or k minus 1 factorial divided by k. Right? So if we have a fraction over a fraction, what we can do is we can multiply by the reciprocal. So in other words, this just becomes k minus 1 fact. And then if we multiply by the reciprocal of k, that's 1 over k. Simplifying that just a little bit more, that becomes, now notice that we have negative 1 times negative 1 to the k minus 1, so that becomes negative 1 to the k minus 1 plus 1, because this has an exponent of 1 affixed to it. And then we're going to divide that by k minus 1 factorial. And you probably remember from the last section, k times k minus 1 fact is just going to turn into k factorial. These negative and positive ones cancel, so we have minus 1 to the k divided by k fact. And that's what we wanted. Because remember, at the very beginning, we said that b sub k was equal to minus 1 of the k over k fact. All right? And then this animal right here, we just had to do a bunch of algebra to be able to simplify that. One final example. Now this is an example where we have two terms. Okay, so a recurrence relation that's predicated upon two previous terms. So let's substitute. Okay, so we're going to start by substituting c sub k. So we're going to plug in k for n. So that just becomes 2 plus k. That's really easy. 2 times c sub k minus 1. That's going to be 2 times the quantity of 2 plus k minus 1. Then we're going to subtract c sub k minus 2. So that's going to be minus 2 plus k minus 2. So again, we're just substituting back in for n, whatever the index is, and we're performing any algebra. Right? So now we hope that this is going to simplify. Right? So this just becomes k plus 1. So we get 2k plus 2 by distributing the 2 minus, this just becomes k. Right? And very nicely, this just simplifies into 2 plus k, which is going to be equal to 2k minus k is just going to be k, so we get 2 plus k. And that indeed works out. All right. So we've gone through and we've looked a little bit about recursive relationships and recursive sequences, and then how they relate to just regular old sequences that we saw back in the section where we did induction, etc. So now we're going to take a look at two different types of sequences. We're going to be taking a look at arithmetic and geometric sequences in the next sequence of videos.